Welcome to this Alan Talks Tech video. If you'd like additional information on my technology videos, please visit my wiki at alantestwiki.pbworks.com. So first of all, let's start with option one. This is basically the standalone LTE, long-term evolution, EPC, evolved packet core legacy architecture. This is the classic architecture of the 4G networks that we're operating with today. The eNodeB has basically the remote radio head end, the antennas, the baseband unit, and a small router to interconnect to other eNodeBs. It's also connected into the EPC, the evolved packet core, with the control plane and the user plane. But now we're moving to new radio, and the front-end architecture of the eNodeB is going to have to evolve yet again. We now have the gNB for the next generation Node B, which is going to support the new radio. New radio is going to operate at much higher frequencies than the traditional eNodeBs that we've been operating with for the last few years. Instead of topping out at around perhaps 5 or 6 gigahertz, we're now going to be entering the realm of frequencies as high as 28, 29, 30 gigahertz, or in the future even higher. In this particular configuration, the gNB is going to have its user plane and control plane connected to the EPC via the eNodeB. This is known as the 3GPP NSA, or non-standalone LTE assisted configuration, or simply option 3. I'm going to go through some other options as well. They're not going to go through in a numerical sequence. I'm going to basically try and get through this in more of a logical progression. I hope it makes sense. There is yet another option. With option 3, we can have option 3A, where the gNB, or the next generation Node B, is connected directly to the EPC, but with the user plane only. The control plane still will have to go via the eNodeB. This allows us to leverage existing 4G deployments. We can create 5G hotspots with the new radio technology relatively quickly, and we can quickly turn up the new 5G services, which are going to require the higher speeds associated with the new radio and the higher performance. Okay, let's take a look at another option. This is option 2. This is a standalone architecture, which is only for greenfield operators. So if you're an operator that doesn't really have a legacy network to worry about, you can deploy the gNB, the next generation Node B, and have it interconnected to the next generation core network with the control plane and the user plane. I'm not going to go into this in this presentation, but the next generation core network is substantially different to the typical EPC, or evolved packet core, that we're operating with today. The biggest difference is that the control plane and user plane will continue to run, if you like, through a separated path through the network. They'll be segmented. This allows us to scale user requirements, capacity requirements, separately from the control plane requirements. It's not always going to be necessary to scale the performance of both at the same level. It really depends on the applications. For example, machine-to-machine communication applications may require the control plane to be scaled more extensively. So for these greenfield operators, they'll be able to fully support the new 5G services with enhanced mobile broadband, offering you very high speeds, massive machine type communications, up to perhaps 1 million devices per square kilometer, ultra reliable and low latency communication, round trip times to the gNB in the millisecond range. But of course, to give us complete coverage, the gNB will have to support a wide spectrum for short range, high capacity throughput, as well as long reach. So different spectrums for different applications. Let's take a look at another possible option. This is again the non-standalone option, but in this case this is option 3A. Here we've got the EPC connected to the gNB, the eNode B, with the control plane and the user plane as we previously showed. But what we're going to do now is we're going to remove the EPC and connect the new next generation node B directly to the new NGCN, or the next generation core network, again using the control plane and user plane. This allows us basically to replace the EPC with the next generation core network. This is for operators who are really driven by capacity, not just the coverage. And this again allows us to use the new 5G services quite quickly. It's also possible, as in the previous example, or a similar configuration with option 4A, to have the eNode B on the user plane connected directly into the next generation core network. Okay, let's take a look at yet another option. This time we're going to simply change the core. So when the new core is available, when the new next generation core network is available, it may be more advantageous for us to simply swap out the EPC, the evolved packet core, for the new next generation core network. In this case, the eNode B will maintain its communication directly to the NGCN, or the next generation core network, and it in turn will be connected to the next generation node B. The next generation node B, of course, will be supporting the new radio and the higher performance associated with it. But remember, for good coverage, we will still need a lot of the technology running in that eNode B. The advantage here with just changing the core is that the network interfaces, routing tables, etc. remain unchanged. So this reduces the impact on upgrading to the new next generation node B and the new radio. So we simply add the new NB via the eNode B. This is actually a less complex upgrade compared to option number 4. Again, we have that other option, in this case option 7A, where we can connect the gNB, the next generation node B, on the user plane directly to the next generation core network. Now, I mentioned during this presentation that we're going to support a wide spectrum for basically different requirements, different applications. In the sub 1 gigahertz range, approximately in the 600 megahertz to 1 gigahertz range, we'll most probably see that part of the spectrum used for machine-to-machine communications and Internet of Things types of applications. In the range of 1 gigahertz to 6 gigahertz, we'll see large capacity vehicle-to-vehicle communications, vehicle-to-X type communications, where very low latency is required, but with good capacity and still fairly good range. In the higher frequencies, in the 6 gig to possibly even 100 gig in the future, we're going to see very high performance. For example, we'll be able to support very high speed downloads of high definition 4K, high dynamic range video, possibly in just a few seconds onto our devices. And we'll also be able to support augmented reality and virtual reality applications, which with much better resolution and quality of experience than was previously possible. Thank you for watching this Alan Talks Tech video. I hope you enjoyed it. If you'd like to get more information on my technology videos with additional material, you can visit my wiki at alantestwiki.pbworks.com. Once again, thanks for viewing.